Are you ready? All right, hi everyone. Welcome. So today we are going to have Argyris telling us about this optimal differentially private sampling. Before that, I wanted to say something. So Argyris has been helping or organizing or co-organizing the seminar for that since I remember at least. He is stepping down, quote unquote, I guess let's say from today. So let's first give him a round of applause for all of them. Thank you. It's been amazing. Thanks a lot. All right.
Okay.
We hear from him.
Okay. So again, everybody on Zoom can see the slides, right? And you can see them also. Okay. Okay, so today I'm going to talk about optimal differentially private sampling from unbounded Gaussian distributions. This work has been accepted for publication at this year's COLD, and it's joined with a very talented undergrad from Waterloo, Valencia, and my advisor, Gautam. So the problem that we will be considering in this work is the following formulation of the sampling problem. So suppose that you have an input dataset consisting of points x1 through xn, which is drawn IAD from some unknown distribution D, which comes from a known cluster. So suppose that you want to output a point Z, which comes from a distribution D prime, such that the total variation distance between D and D prime is at most alpha. So suppose that we don't care about privacy, which is what I mentioned in the previous slide. How would you solve this problem? Yes. So without privacy, you can just output any point in the data set, so the problem is completely trivial. With privacy, however, what you need to do is synthetically generate a new point in a way such that privacy with respect to the input data set is guaranteed. So the particular definition, the particular version of the definition of privacy that we will be using is approximate differential privacy, where formally what this definition says is that if you have an algorithm which receives n input data sets, we say that the algorithm is epsilon delta differentially private, which means approximate differential privacy, if suppose that you have any pair of neighboring data sets, x and x prime. So neighboring here means that the Hamming distance between these two data sets is at most 1. And also suppose that you have any subset of the output domain of the algorithm. Then what you want to happen is that the probability that the output of the algorithm under input x falls into the subset of the output domain that you're considering is upper bounded by e to the epsilon times the probability of the same event under input x prime plus delta. So roughly what this means is that you have these two data sets which are adjacent and say they differ only at the ith entry. And this implies that the two distributions that you observe at the output are close to each other. So I have a number of remarks related to this definition. First remark is that this is a worst case guarantee in the sense that, your algorithms, they might have, in addition to the privacy guarantee, some utility guarantee. So depending on the problem, the utility guarantee might fail. But the privacy guarantee is worst case in the sense that you want it to apply to any pair of neighboring data sets. And in addition to that, when it comes to the delta parameter, so if we assume that delta is equal to 0, which is referred to in the literature as pure differential privacy, then this would imply that taking the ratio of these two probability terms is always upper bounded by e to the epsilon, where if we fix epsilon, we have a constant upper bound on this density ratio. So the idea is that if delta is greater than 0, we tend to interpret it as some small probability that the ratio between the two events ends up exceeding e to the epsilon, which essentially amounts to, a sort of failure event, really. So, having said that, let me mention some prior work on the topic of private sampling. So this is a fairly new research area. Basically, the model was introduced in a work by Raskolnikova, Kumar, and Swanberg, which appeared in Europe's 2021 and more recently in Cyclone 2025. So that work, which introduced the model, focused on classes of discrete distributions, so no Gaussians, which is what, based on the title, we will be focusing on. But then there was follow-up work by Ghazi, Kumar, and Manurangsi, which appeared in Europe's 2023, which considered Gaussians, but it gave three separate algorithms where these algorithms, they applied to increasingly general settings. And the two more general algorithms were suboptimal. So as a matter of fact, who here is Shah, who is a prof at Waterloo and gave a talk at our seminar back in October. So the last paper that I want to mention is a more recent work by Albert Chu and Differentially, which appeared in this year's ALT, which considers the problem of multi-sampling. So in our model, we just want to output one data point, which is close to the input distribution, whereas for multi-sampling, you want to output, say, k points such that their distribution is close to the k-fold product of the input distribution with itself. So we won't be considering this here, just mentioning to give you a sense of what the state of the art is on this question. So what we need to talk about a bit is the results given in the work of Ghazi et al. So because of that, I have a table which basically features three classes of distributions: Gaussians with unknown mean, but non-covariance matrix, which without loss of generality we assume to be the identity, then Gaussians with unknown mean and unknown covariance matrix, but the covariance matrix is spectrally bounded between the identity and kappa times the identity, where kappa is a parameter which we assume that we have access to. And then is the class of general Gaussians in d dimensions with no bounds on the parameters whatsoever. So there's three problems here which are relevant. The first is the problem of learning without privacy guarantees, for which there exists some folklore sample complexity results, all of which share a common pattern. So in the sample complexity results, we have a numerator, which is the number of parameters, which in the non-covariance case is d, and in the unknown covariance case, it's d squared. And there's also a dependence on the target error, which is 1 over alpha squared. Then there's the question.
Before you go there, don't get it. If kappa is why is kappa not appearing in d square over alpha square?
So we'll get to that eventually. We'll get there, because that's actually an important point in this work. So,
But okay, but just to understand, what does theta then means? There exists a kappa such that this requires d square alpha square.
so no, the idea is that at the input, instead of just receiving a data set, we also receive an upper bound kappa on the eigenvalues.
Sure, but when you write theta, it means that it's also an omega. So you also need these many samples, etc.
Yeah, but so eventually the idea is that in the sample complexities in the first two rows, kappa does not appear anywhere, whereas it appears in the third row, and it's not really necessary for kappa to be there. And our work is basically about removing that kappa dependence.
So good. So, but that's my question. In the second thing, if kappa is not appearing, you're proving that, or you're stating there is an omega d square over alpha square. And is that omega, is that your bound for all choices of kappa, or there exists some large choice of kappa that this is?
I think we should apply for choices of kappa.
Then set kappa equal 1, and that contradicts the first. That's the confusion.
Okay, I'm sure I understand that it's some notational issue.
Okay.
I guess the second and third column focus on learning both the mean and the covariance, like estimating the entire distribution. Whereas the first column we focused on learning the mean itself. But
Except that. No, I still don't understand. If kappa is one, then you actually do know the covariance.
oh, I see.
Yes,
I
it's
see. So,
exactly equal to the identity of kappa is one.
right, yeah. The second column, I guess, is uninteresting if that equals one, but I think like when two equals two, then.
Yeah, so
Like counted away from one by a constant.
yeah, like kappa could potentially be, I don't know, 2 to the d say, 2 to the dimension.
No, I understand, so yeah, but at two already it becomes hard, or is it like 2 to the d that makes it?
Oh, yeah, no, you generally need to consider large values kappa.
No, I think I thought for the lower bound at least to get to d squared rather than d, I thought it's just like the construction has just somewhere between 1 and 2.
Right. Right. Yeah.
I think even with like, 1 and 1.01 or something, like as long as there's some essence constant, yeah.
And here you have to go to the covariance matrix and,
For the first two rows, yes.
So going back to what I was saying, these are the sample complexities for non-private learning. Whereas for learning with approximate differential privacy, the pattern that the results follow is that you have the sample complexity for learning without privacy, plus an additional term which has to do with the extra cost of privacy. So when it comes to the cost of privacy, you again have the number of parameters, but this time it's not divided by alpha squared, but rather alpha times epsilon. So in the last row, we have the results for sampling from Ghazi et al. And the idea is that, let me mention that, in all of the sample complexity results, there's supposed to be some delta dependence, which I'm hiding, but it's not super important. It's basically polylog 1 over delta. So let me now give you some insight about the results of the sampling. So as you can see, when we're doing mean estimation, the sample complexities are linear in the dimension. However, when we're doing sampling for the class of distributions with known covariance, the dependence on the dimension grows from d to square root d. So this is an important improvement, which, it manifests in the case of non-covariance, and the question is to which extent we can actually get this in the case of unknown covariance too. The second thing to note has to do with the dependence in 1 over alpha, where in all the estimation tasks, it's polynomial, whereas for sampling, you get polylog in 1 over alpha. And the last thing to note, which is an important point of this work, as I mentioned, is that when we're doing sampling with non-covariance matrix, sorry, not known, but covariance matrix that is unknown, but we have known bands, the algorithm that they give in Ghazi et al., it features a quadratic dependence on this kappa, which is the upper bound in the eigenvalues, which, however, does not appear at all in the sample complexities for the corresponding learning tasks. So the question is to which extent this dependence is actually necessary. The thing is that we have this dependence, but at the same time, we have some savings in D where the dependence is linear instead of quadratic. So we observe the same effect as in the mean case where we had a quadratic improvement from learning to sampling. So the thing now is that if we don't assume that we know such a kappa, in the third column, we get d squared again, which is the sample complexity for learning. So essentially, to summarize all of those remarks, I'm going to state what the main open problem from Ghazi et al. Is. So the question is, can we design an algorithm for sampling from general Gaussians, that is Gaussians with no assumptions on the range of the parameters, such that we have both linear dependence in the dimension, no dependence on bounds on the condition number of the underlying covariance matrix and polylogarithmic dependence in 1 over alpha. So going back to this, we want to get D here, but at the same time, we don't want to have kappa squared. We want the upper bound to be independent of it like this here. And at the same time, we want to maintain the polylog over alpha dependence. So our result is that there actually does exist an epsilon delta differential private algorithm, which if you give it IID samples from a Gaussian with arbitrary parameters, where the number of samples is big O of log 1 over delta over epsilon times D plus log of log 1 over delta over alpha times epsilon, then this algorithm will output a sample from a distribution which is alpha close in t distance to the underlying distribution. So as you can see, we have both linear dependence in D and no bounds on the underlying distribution on its parameters, and we have the log 1 over alpha dependence here. So in that sense, it's a best of all worlds kind of result, which also nearly matches a lower bound given in Ghazi et al. So if
what's the lower bound of?
sure what?
What is the lower bound of Ghazi et al?
So they say that if you assume that you have a covariance matrix that's bounded between the identity and 2 times the identity, then you need omega of D samples to sample from the distribution. Okay.
It's 1 over epsilon. So your dependence is D over epsilon.
So actually, wait, no. Wait. No, I might be slightly wrong. So the lower bound, the full lower bound is, I think, D over log D times epsilon. So the epsilon is the denominator, yeah. And I say you imagine here because you know that log D is the denominator, which I forgot to mention earlier. So as we move on to the technical stuff, let me start by mentioning one key insight, which is going to be like a core theme in this work, which has to do with how sampling connects to estimation. So the key observation that you need to have in mind is that private sampling is really just private estimation, but with a weaker guarantee. So when you're doing estimation, you want your distribution to be close to the underlying ground truth, like you're going to produce a distribution of the output, which essentially translates to parameter closeness. Like you end up doing estimation and you produce some parameters which are close to the parameters of the data generating distribution. For sampling, on the other hand, you just output a single point, not a distribution. But the idea is that the process that produces this one point amounts to instantiating estimation algorithms, but in a slightly weaker regime, so to speak. So this is going to be more precise as we go along, but what you need to keep in mind in order to understand why sampling is generally easier than estimation, like they are connected, but it's easier, is the following. Suppose that we perform estimation. What we will end up with is some pair of estimates mu hat and sigma hat, which will be produced by a private algorithm. So what we can do then is take these two estimates and plug them into a sampler from a Gaussian distribution, and that way we can produce an infinite number of samples without privacy loss. So the idea here is that there's a property of differential privacy that tells you that if you have a private algorithm, you can take and post-process its output, and there's not going to be any privacy loss. So yeah, as long as you're not touching the data set itself in any of the post-processing steps, you're fine. So If you have those two estimates, you can plug them into a sampler from the Gaussian distribution, and you can generate an infinite number of samples. This is in contrast to sampling, where you just want one sample. So the desired guarantee in that sense is weaker than estimation. So it is precisely this difference that I just highlighted, which is the source of the savings in the sample complexity. So we will be doing estimation, kind of, but with weaker guarantees, which will eventually allow us to save in the sample cost. Is that clear? Any questions?
Just a tangent, because you mentioned multiple samples. So what this means is, if I know I need what, D samples, I'm better off just learning than running this algorithm.
Yes.
If I just want one sample, you just want to do your algorithm. What happens in between?
So yeah, that's basically what the multi-sampling paper by Chu and Nayak considers. But as far as I recall, the sample complexity bounds that they gave in the paper were not tight. But the idea is that what you would want is that if you have k samples, it should somehow interpolate between the two regimes, essentially. Like the k parameter should appear in the sample complexity somehow, where after a point, if k becomes large, you're just going to get the sample complexity for learning. Because
and do we know if this would happen at D samples, or if you could still have some savings as well?
So I can't say for certain, but intuitively it feels like the right thing would be for this to happen at D samples. But this is not a formal argument. I haven't thought of this question, but intuitively it feels right.
Sometimes we can learn also with overlap for samples.
Yes. Yes. So actually what you just mentioned is the idea behind the lower bound that I'm referencing here. Like basically the idea is that to obtain the lower bound for sampling, they're reducing from a lower bound on covariance estimation, and they're implementing some idea which is roughly what you're describing. Any other questions? Okay, so what I'm going to do now is make a first attempt at making the connection between sampling and estimation more precise. And to do that, I'm going to use as an example the sampling algorithm for the non-covariance case from the work of Ghazi et al. So what the algorithm does is the following thing. You start with n prime samples, where n prime is below tilde of square root d over epsilon, and you run a histogram algorithm over those samples in order to get a coarse estimate for the mean. So what histogram algorithms do basically is the following. You have some domain which you partition into a set of histogram buckets, and what you want to do is identify what is the most populous bucket. So the idea is that you basically put your samples into the buckets, and then you add the noise in order to privatize the whole process of identifying the most populous bucket. So depending on what kind of privacy guarantee you want, the implementation of this last step might be slightly different. If you want delta to be equal to 0, so pure differential privacy, you need to add noise to all of the buckets, and the noise will have to be Laplace noise. If you want, however, privacy, like approximate differential privacy, so delta is positive here, you can get away with adding noise only to the non-empty buckets, and you can have Gaussian noise instead of Laplace noise. So the idea is that since we are dealing with Gaussian distributions, they have very strong concentration properties. So you would expect the most populous bucket to be the one that contains the mean, really. And you can use that in order to get a coarse estimate for the mean, which is mu0, and it's at L2 distance at most roughly square root d from the true mean. So once you do that, What you do is that you draw a fresh set of samples. The reason why you do that is because you want the new samples to be independent from the ones that give you 0. And for each of those new samples, which their number is square root of d plus log 1 over alpha epsilon divided by epsilon, you truncate it into an L2 ball, which is centered at your coarse estimate and has radius square root of d times log of n over alpha. So once you do that, you take the truncated empirical mean and you add Gaussian noise to it. So any questions about this algorithm? It's basically an estimation algorithm, but instantiated in a slightly different parameter range to the point that the guarantee that it gives is weaker. So
what you do again, so you then mu of the root the other different,
yes,
then you put a ball of radius root v roughly around this mu, and you're truncating every point that you get, you're truncating to v. Like you're not projecting, you're like literally just truncating.
yes.
Okay, so you get one of your points and then you just add one of those points.
No. We take the truncated empirical, we take the truncated empirical mean of the points and add Gaussian noise to it for privacy.
When you write 1 over n times that, does it mean you sample one of them uniformly at random?
No. It's a linear combination.
Oh, you sum them off these points
Yes.
and.
Truncated empirical mean. Yeah. So
Can I ask a question about the previous slide?
So sorry, what did
Can
you
I
say?
ask a question about the previous slide?
Yeah.
Can you quickly just maybe very quickly mention what is epsilon delta dB histograms?
This is going to become clear in a bit. Okay.
Okay, cool. Okay, thank you.
So this has to do basically with the fact that you want to truncate the data set. And if you didn't use the histograms, you wouldn't be able to truncate, but we'll see why truncation is necessary. So as I was saying, there's two guarantees that one needs to establish. It's the utility guarantee, which is that the TV distance between the distribution of the output point and the data generated distribution is at most alpha. And the second thing is that the output must satisfy epsilon delta differential privacy with respect to the input samples. So related to the utility guarantee, I'm going to give an argument which is not really formal, but I will claim at the end that it's possible to formalize it. So let's pretend that we're not doing truncation. There is the stability property of the Gaussian distribution, which tells you the following. You have a bunch of independent samples from a Gaussian distribution, and if you consider any linear combination of those samples, the distribution of the result is also going to be Gaussian. So if you do 1 over n times sum of n IID points from a Gaussian with mean mu and identity covariance, then the resulting empirical mean will follow a Gaussian distribution whose mean vector is the same mu as before, but the covariance matrix is 1 over n times the identity. So if you take that and you also add Gaussian noise to it with mean 0 and covariance that's n minus 1 over n times the identity, then the distribution of the full result is going to be a Gaussian with mean mu and identity covariance. So the thing is that what we want to do essentially is get something which is close to this behavior, but with truncation. So the idea is that we choose our truncation radius to be large enough so that Chernoff bounds end up implying that with probability at least 1 minus alpha, no point is affected by the truncation operation. So roughly the intuition behind the result is that, with probability 1 over alpha, truncation doesn't really do anything to affect the distribution of your data set, but there's a small probability alpha where, points could be affected in an arbitrarily bad way. Now, the thing is that this is not a formal argument to up or down the TV distance, and the reason is the following. When you're conditioning over the occurrence of the good event, which is that no points are affected by the truncation operation, then this essentially affects the distribution of the input data set. So if you are conditioning over here the fact that the zi's which are produced after the truncation are the same as the xi's, there's a conditioning happening there which affects the distribution of those points. So you can't treat them exactly as Gaussian points and apply stability to them. However, I claim that despite this, you can do a formal proof of the argument which goes through the joint convexity property of the TV distance. So, any questions about the utility guarantee?
It's the coupling happens. So suppose you run this algorithm without doing truncation, and as you said, you'll get a good sample. And the truncation only happens with probability alpha.
Yes.
So can't these two distributions just be coupled with each other and say that you have to pay another alpha in the distance between?
Yeah, I believe what you're describing is roughly the idea of the proof, essentially. So, and now in terms of discussing the privacy guarantee, I'm going to describe essentially where the truncation operation is necessary to begin with. So the thing is that if you want to privatize a statistical quantity which you evaluate over some data set, then it's a folklore observation that you might want to add spherical Gaussian noise to it, where the magnitude of the Gaussian noise is calibrated based on the sensitivity of the statistical quantity that you're calculating. The thing is now that during the privacy analysis, we treat the data set as a worst case, because in the definition of privacy, we said we want the guarantee to hold for any pair of neighboring data sets. So when it comes to Gaussians, we know that they are supported over all of d-dimensional space. So if we're doing a worst case analysis, when calculating the sensitivity of the empirical mean, we need to consider what happens if you have one point in the data set and you replace it with another point, which is, say, at infinity. So if you're not truncating, then things, can go catastrophically bad at that point, which is why you need to truncate, and it's why you need to do the approximate DP histogram step, which we mentioned earlier. So the idea is that our choice of parameter is such that adding noise that has magnitude n minus 1 over n suffices. So, the utility guarantee goes through, the privacy guarantee goes through, so we're good with both. So, to summarize, we saw that we had an algorithm for sampling from distributions with non-covariance matrix, and the pattern was the same as that of a private mean estimator. But we had a weaker guarantee in terms of what we want the output to satisfy, rather than relative closeness of the output point to the true mean. The d-dependence in the sample complexity came from the truncation radius. So the result, we have square root d here, and the truncation radius here is square root d also. So that's basically where the square root d comes from in the sample complexity. And at the same time, when it comes to the polylog 1 over alpha dependence, it has to do with the fact that The polar log 1 over alpha dependence has to do with the fact that, in contrast to estimation, alpha does not correspond to quantifying closeness of parameter vectors. Instead, it only corresponds to the probability of the bad event in this analysis, which is that that one of the points gets truncated. So the question now is what our approach is for the general case where we have an unknown covariance matrix. So our initial attempt was the following. We said that, okay, for the non-covariance case, people assume that the covariance matrix is always the identity. Now, since we don't care about the mean, but rather what happens for the non-covariance, let's pretend that the mean is known and equal to 0. So let's first try sampling from a Gaussian distribution with mean 0 and covariance matrix sigma. So what we attempted to do is basically instantiate a covariance estimation algorithm and maybe post-process its output appropriately in order to, instead of getting a matrix, maybe produce a vector from it where the distribution of the resulting vector will be close to this Gaussian. The thing is that, although there appeared to be evidence that the approach we were trying can work in principle, we would lose the polar logarithmic dependence in 1 over alpha. So we would have exponentially worse dependence in this parameter, which is why we had to abandon this approach. Instead, the correct approach, which led us to our full result, has to do with combining 2 other algorithms. So the first algorithm is that of Ghazi et al. For the case with unknown but bounded covariance. And the idea is that we combine this algorithm with an algorithm for covariance-aware mean estimation, which is due to Brown et al. So I'm going to describe each of these algorithms. I'm then going to describe how one combines them together. And then I'm going to briefly give a sketch of the analysis. So let's start with the algorithm of Ghazi et al. For the bounded covariance case. So this algorithm we actually need to go over in detail. So we'll be talking about it line by line. So first observe that you have a data set which is of size n1 plus 2 times n2. The idea is that the first n1 samples, they correspond to one subset of the data set, and the last 2 times n2 samples, they correspond to another subset of the data set. These 2 subsets are disjoint, and we're going to do something different with each of them. Before, however, doing different things with them, we truncate both of these subsets of the data set, and the truncation operation is what requires knowledge of kappa there. Then we take the points in the second subset, we consider them in pairs, and we subtract the points in each pair. So the idea is that if we weren't doing truncation, this operation here would result in a sample from a Gaussian with mean 0 and covariance matrix the same as the original Gaussian. Now, the interesting stuff starts here. So this step of the algorithm says that you draw a number from a distribution which is called a shifted and truncated Laplace distribution with appropriate parameters. And then there's a check that you want to do in a private manner. So there's a typo here in the algorithm, which is from the paper that I got this from. Here, this inequality should say less than or equal to rather than greater than or equal to. So what is this saying? This says that you have your recentered points, you form the corresponding empirical covariance. So if you divide both sides by n2 here, you would have you would have the sum divided by n2, which is the truncated empirical covariance. Okay. So the idea is that you want to privately check if the smallest eigenvalue of the truncated and recentered empirical covariance is smaller than 0.75. And if that is the case, the algorithm's execution aborts here. So roughly what this check is doing with the minimum eigenvalue is basically trying to see if these truncated points here span the whole domain. It's not clear yet what the usefulness of this is, but I'm going to get to that in a bit. What you need to keep in mind, though, is that it's at this step of the algorithm where the assumption that sigma is spectrally lower bounded by the identity comes up. So the last step says the following. It says you have n2 samples after this operation you did on the second subset of your dataset. Take a unit vector, a uniformly distributed random unit vector from the sphere in n2 dimensions, and take these points and do a random linear combination of them where the weights of the linear combination come from the vector that you sampled in the previous step. Once you do that, you take the first subset of the data set which we have been ignoring really so far, and calculate the truncated empirical mean, and then add to it a rescaled version of the random linear combination of the second subset of points that you have. So the thing is that the claim here is that this algorithm has both the desired utility guarantee and the desired privacy guarantee. Now, the utility guarantee, it's not much different, like to establish it from the known covariance case. But how is this private? Because what we said earlier is that you have the statistical quantity that you're calculating, and then you're adding Gaussian noise to it, which is data independent. But here, you're saying that I take this random unit vector, I do a random linear combination of a separate part of the data set, and somehow this gives privacy. So, what's going on here seems to be completely different from the template that we have in our heads for private algorithms.
So is both of B and delta here, capital delta?
So wait, B here has to do with your truncation radius. And delta, I think it's supposed to be some proxy for sensitivity, essentially.
Sensitivity of what?
Sensitivity of the minimum eigenvalue. But I'm not entirely sure about that.
The B is a function of capital here? or-
Yes, yes.
And delta is something.
So this algorithm here assumes that you've done the private histogram step first, so you have the course estimate for the mean and everything. So the truncation operation is with respect to a course estimate, and B is supposed to be the radius. So having said that, let me describe what's really going on in terms of the privacy guarantee here, which is the non-trivial idea really. The key insight can be summarized as you're using the samples themselves to noise the output somehow. Like we took the samples, we did a random linear combination of those, and that gave us privacy. So the idea is the following. Suppose that the samples are linearly independent and truncated to some bounded domain, which is what we did. then the random linear combination operation that we did, it can be described as this product of two matrices where the first matrix has the truncated and recentered points as columns, and the second is the random unit vector that we have there. So if the input data points after truncation and recentering are linearly independent and live in a small domain because of truncation, then the distribution that you get because of this operation here, where you multiply the matrix with the random unit vector, it cannot change much if you change one data point. So the thing now is...
Sorry, I don't get this intuition at all. You're saying I want to linear independent points,
Yes.
and I pick something in their span, for instance. And you're saying if I remove one of these points, then the distribution of the outcome doesn't change.
So let me say the following thing. Let's understand first why the linear independence assumption is required. Suppose that instead of having a linearly independent set of vectors, they were linearly dependent. And let's take the most extreme case of that. The most extreme case would be that you have a data set where all points are 0 except one point. But the thing is that for this data set, if you did a random linear combination here, the result would always be that one non-zero point, essentially, multiplied by some number. But the idea is that you would directly get to observe one sample at the output, essentially. And if you change that one sample, then whatever you change it to, then if you repeat this operation, you will get the other sample that you replaced your original one with.
Do you assume when you change it, you again get something that is linearly independent or not?
So wait a moment. When you change it, you get a new data set where all points are 0 except this one point. And you want to see how the distribution changes at the output after you do this. So it doesn't matter if the new point is linearly independent from the original point, if that's what you're asking.
Got
In any case, the assumption about linear independence is there basically to ensure that what I just described about getting one point directly at the output doesn't happen, essentially. So the idea is that if that assumption holds and is combined with a truncation operation, then changing one point will not affect the distribution of this thing significantly. And this step here, where you privately check what happens with the minimum eigenvalue, it says that, okay, we know that all of the eigenvalues are at least 1, but the thing is that since we are looking at the empirical covariance, maybe in the empirical covariance, the minimum eigenvalue could appear to be somewhat smaller. But we expect that it won't be much smaller. It will be at least 0.75. So that's why we do this step here. Like basically this step ensures that if your algorithm reaches the point where this happens, the data set that you have is sufficiently well behaved to ensure that the privacy analysis of this step goes through. So, did that make sense?
Often this, that would really this one.
Yes.
Often this, often, this will be satisfied.
How often it would be satisfied? So I claim that this will be satisfied with probability at least 1 minus alpha. Due to the choice of parameters and the concentration properties of the Gaussian. So the idea is that, this gives us the desired privacy guarantee, but with a quadratic constant copying the sample complexity, and it also gives us the utility guarantee, even though I haven't talked about the utility analysis because it's fairly simple. But the question is if it's possible to implement this algorithm without any bounds, any prior bounds on the underlying covariance matrix. So to do that, we need to talk about covariance aware mean estimation, because this is really where the required tools will come from. So suppose that you have an IID dataset from a general Gaussian and you want to do mean estimation. So a general Gaussian in the dimensions, its density is like this. And the idea is that if you consider points for which this x minus mu norm with respect to sigma quantity is constant, the points represent an ellipsoid. So let me describe this in a bit greater detail. This sigma norm that I have here, which is the Manurangsi norm, is basically a rescaled version of there should be 2 instead of sigma. So this is a rescaled version of the L2 norm, where what you do is that you have the distance between x and the mu, but you multiply it by sigma to the -1/2, and then you take the L2 distance of the resulting vector. So if you want this thing to be a constant, you're basically asking when is this quadratic form a constant? So the idea is that if you plot the points which satisfy this equality here, they turn out to be an ellipsoid whose axes are basically determined by the eigen decomposition of their covariance matrix sigma. So roughly the idea behind this is the following. If we were in a single dimension, you have the variance of the Gaussian, which tells you how spread out your Gaussian distribution is. But in multiple dimension, there's different directions, and the extent to which your Gaussian is spread out in different directions has to do with the geometry of the covariance matrix sigma, as that geometry is captured by the eigenvalues and the eigenvectors of the matrix. So the idea is that when you're doing mean estimation with unknown covariance matrix, you would want to quantify the error in the metric which takes into account the directions along which your Gaussian tends to be more spread out. So if there's some direction along which the variance is high, you want to be more lenient in terms of how to quantify the error. Whereas if you have some direction of very low variance, you want to get an estimate for the mean, which is very close to the true mean along that direction. So because of that, this rescaled version of the L2 distance called the Manurangsi distance is what we want to use to quantify the estimation error rather than the vanilla L2 distance. So this norm has the advantage that it's affine invariant if you do an affine transformation of your Gaussian. So having said that, suppose that you want to do this covariance aware mean estimation thing without privacy first and with privacy later. So without privacy, what you could do is first use d over alpha squared samples in order to get an estimate for the covariance which is close to the true covariance in rescaled spectral distance. Then you draw a fresh set of samples and you rescale them using the estimate that you produced in the previous step. So the thing is that the rescaled dataset that you get, it's going to come from a Gaussian which is near spherical, like the covariance matrix is going to be very close to the identity. So what you can do then is take those rescaled samples and take their sample mean, and you'll get something. Oh, over here, I should have sigma hat in the -1/2 times u. Nothing. Sorry. So you'll get something which is close to the mean of the rescaled distribution, which is near spherical. Okay. And then if you take your estimate and you multiply it by sigma hat to the 1/2, you'll end up having a final error, which is, okay, from here, you might be able to error. I've made some mistake here. I've made some mistake in the slide. There are some typos, but the idea is that if you first do a spectral estimate of the covariance and then rescale the points, this eventually can give you a valid estimate, which is close in Mahalanobis distance. And the overall number of samples is going to be d over alpha squared, so that's the bottom line. Don't get confused by my typos. So the thing is that the strategy that I just described, if you try to implement it with privacy, it fails. This has to do with the fact that there's a lower bound that tells you that spectral estimation needs d to the 1.5 samples, which, as a matter of fact, this lower bound was proven in the paper by Gaussian, myself, and Baker, who at the time was doing his postdoc here. So the thing is that essentially what people in the private covariance aware mean estimation literature are trying to do is essentially bypass this d to the 1.5 lower bound. And there have been a number of works which have been getting a dependence in the sample complexity that's linear in D by avoiding this step of estimating the covariance matrix private. So there were two such works. The first was computationally inefficient and it was by Brown, Gabardi, Smith, Ullman, Mouzakis. It was in March 2021. And then there were two concurrent and independent works by Brown, Hopkins, Smith, and Ducci, and Pudi, where both of these works appeared in Coles 2023 and were awarded Best Student Paper Awards. So the idea is that we're now briefly going to talk about the algorithm of Brown, Hopkins, and Smith, which is the basis for our result. So what this algorithm does is the following. You take your input data set and you run some stable estimators on it. So stable estimators, what they do is that
Wrap up.
yeah, I'll try to wrap up in the next 5 minutes or so. So stable estimators, what they do is that you want to do basically the empirical mean and the empirical covariance, but instead of assigning uniform weights 1 over n to all of the points, you assign weights which are proportional to the percentage of points that each point is close to. So you have your data set. If you have a point which is really, really central and all the other points are close to it, it's going to have large weight. Whereas if you have a point which is an outlier, you're going to assign small weight to it. So that's what stable estimators do. And then the idea is that if your data set is well behaved, then you can sample a point from this Gaussian here, which amounts to saying that I'm taking the stable estimate for the mean and adding to it Gaussian noise, which has been rescaled using the square root of the stable estimate for the covariance. So the idea is that you're adding Gaussian noise, but it's not spherical, but rather it's Gaussian noise, which has been rescaled using an estimate for the covariance, which, however, is non-prime. So if your data set is sufficiently well behaved, which is checked in this proposed test release step, then you get to output something which is both correct and private. So let me mention that, this algorithm here, it cannot resolve the sampling question, even though you sample a point from a Gaussian in the last step. And the reason is that if you wanted to use this algorithm, you would again get a polynomial dependence in 1/alpha. So you need to do some modification, which amounts to combining it with the Ghazi algorithm. So the idea is that we take the Ghazi algorithm, but instead of doing the truncation operation that it did, we use the weights which are produced by the stable estimates of the Brown et al. Algorithm for covariance over mean estimation. And these weights, since they are small for points which are outliers, they basically correspond to a soft outlier removal operation. And because of the fact that we do this, we replace the PTR step of Ghazi et al. With the PTR step of Brown et al. PTR is basically this private check thing that we need to do. So this is the overall algorithm. Like this part is the same as the Brown et al. Algorithm. And this part here is basically a version of the Ghazi et al. Algorithm, but one that uses the weights from the stable algorithms. So this is the utility analysis, which I'm not going to describe, but it follows basically the same pattern as the previous case. Just, the events that you want to be satisfied for the analysis to go through are these events here instead of all the points being close to the true mean. So that leaves the privacy analysis, where for the privacy analysis, all the randomness comes from this random unit vector. And to analyze the behavior of the output, assuming that the PTR step succeeds, the key quantity of interest is the hockey-stick divergence. So the hockey-stick divergence is a generalization of the TV distance, and it gives us a succinct way of describing the definition of privacy. Basically, the idea is that the TV distance you can define as max overall subsets of the domain probability that P assigns to the subset minus probability that Q assigns to the subset. But here there's an additional e to the epsilon multiplicative factor. So if epsilon is 0, this gives you the TV distance. But if epsilon is greater than 0, then you can use this to describe the definition of approximate differential privacy, where here I have alpha, it should be delta. Like if you have epsilon delta TP, then the hockey stick divergence for any pair of adjacent data sets is at most delta. So the idea is that we are using properties of this in order to establish our privacy guarantee. And yeah, I have basically 3 slides here which describe the ideas in the calculation. The calculation is really long. It's like 15 or 20 pages. But yeah, I don't know to which extent I have time to go over this proof sketch. So in terms of some conclusions, we optimally resolved the question of sampling from general Gaussians. The question is, there are some open questions. First, we assume that delta is delta is greater than 0, which it made some things easy for us. Various of the techniques that we used are specific to approximate differential privacy. So the question is, what happens with pure degree? Then there's the question of doing optimal multi-sampling because the Cho and Nayat paper is not optimal. Then there's the question of whether it's possible or interesting to extend to more general classes of distributions. Then there's the question of whether there's a connection to robustness. So if part of the dataset is corrupted, whether it is possible to sample a point from the underlying distribution despite the corruptions. And there's also one thing that I have here, which is something that we may end up adding to the archived version of the paper. We think that as a consequence of this combination of the two algorithms that we did for the solution, we might have an alternative to the Brown algorithm, which is basically an instantiation of our algorithm with slightly different parameters. So yeah, that's the end of this group.
Student over on, there's one quick question.
Okay. So we're going to stop the recording.
Well, this time the order is second.